All right, so this entire section is about rational functions. What is a rational expression? What is a rational expression? An expression that can be written as a fraction. Now, a rational number is a number that can be written as a fraction. So the term rational clearly indicates to us that we're looking at something to do with a fraction. Okay? Something to do with a fraction. So if we start with a rational function, clearly it's any function that can be written as the ratio of two functions. What's a ratio, though? What's another word for a ratio? A fraction. So the same thing we've been saying. So you hear a rational function is the ratio of two polynomial functions. All it means is it's a fraction. There's something in the top with a variable, something in the bottom with a variable. End behavior. The term end behavior simply means what's happening to the graph as x gets bigger and bigger and bigger. For example, what's the end behavior of a graph like this? As x gets bigger and bigger and bigger, is the function going up or down? Just follow the sign. Which way? Up. Okay, again, I move to the right. As x gets bigger, focus up here. As x gets bigger, the function is getting larger and larger. It's going up. As x gets smaller, the function is going down. What's happening in the middle there?
That's what transition would be.
Yes, transition. But I'm talking about the end behavior, right? So do I care about the middle? End behavior is referring to the ends of the function. So that graph would have the same end behavior as this graph, wouldn't it?
Yeah.
Agreed? What about this graph? Right? Same behavior still. All of these graphs have something in common that we're going to see. Okay? Hypothesize, if you'd like to, for now in your head. There's something in common amongst these three graphs. There'd be something in common if all these graphs did the same thing, but instead of rising, if they all fell. If they did this, and the next one did this, and the next one did this. There's also something in common. Okay, so we're going to talk about that, but that's what end behavior is referring to. As the independent variable goes to positive or negative infinity, meaning x, as it gets bigger and bigger in each direction, is it going up or is it going down? Third, discontinuity. Ryan, read that for us.
When a function is not continuous at a specific point.
Yeah, when it's not continuous at a specific point. What's a discontinuity then? Where have we seen them before? We've seen them. It's not on a graph. I'll give you a hint. Well, it's not on a two-dimensional graph.
Is it on like a number line?
On a number line. Remember we've seen this on a number line before? What if the answer is all real numbers except for 7? How would you graph that? Well, here's 7. You'd put an open circle, and you'd shade everything right, and you'd shade everything left. So we represented a discontinuity with, what is this? An open circle. So in a graph, you might see what's called an open circle. So imagine a graph up here. I'll use the same graph at the top. Actually, I'll go down. It's called a hole. It's a hole in the graph. It's possible to have a hole in the graph. And I'm sure you can hypothesize why. What would restrict our x values?
Can't be over 0.
Remember, you can't have a 0 in the denominator ever? So if there's an x in the denominator, some value of x would make the denominator 0. That would cause it to go a hole. Or, we're going to see something in a moment that's called an asymptote. And that exists on a graph if the graph looks like this. Okay, maybe what's happening here is there's some imaginary vertical line. This is called a vertical asymptote, at which the graphs want to be closer and closer to, but they're never going to touch that location. Maybe that location is x equals negative 1. If that happened, it's because x plus 1 would be in the denominator. If you have x plus 1, visualize, please. You have to close your eyes, do it. Imagine x plus 1 in the denominator. If I plug in a negative 1, I get negative 1 plus 1. What is that? 0. When the denominator becomes 0, the function is undefined, you have a tendency to get what are called vertical asymptotes. So these are types of discontinuities. Okay, but an asymptote is a line such that the distance between that line, or between the curve and the line, approaches 0 as they tend to infinity. So this little gap here, how far away is this? Give me a number. Estimate. If this is negative 1, what might this be? Okay, if this is 3 and this is negative 1, what's the gap? 4. What's happening to the gap as I get closer and closer here? Yeah, so the distance between is getting smaller as it tends to infinity. In this case, tends to negative infinity. Either one. Depends on the graph. Okay? So an asymptote is something that gets closer and closer. Here's an example of an asymptote. I start here. I walk halfway to the wall. So there's halfway. I stop. What if I walk halfway again? Where's halfway now? Maybe it's like right here. I'm going to the cabinet. Then I walk halfway again. Mike? Why not?
Because you always come halfway. It's easy.
Where did you learn this before? In what subject?
Last year.
Algebra last year?
Earth science, half-life, and yeah.
Both. Algebra last year and earth science. Okay? Half-life. That's what a half-life is. Technically, it never goes away. That's what an asymptote is. An asymptote is radioactive decay. The radiation, the mass percent radiation does this in a half-life graph. But it tends to do this again, right? Because it never really becomes non-radioactive. So that's an asymptote. In that case, the x-axis would be the asymptote. Again, think about a graph of percent radiation. After one half-life has occurred, how much percent radiation do you have? 50. So here's at the start. So this must be one half-life right here. Okay, sometimes indicated by T star, you'll see on like science books. So that's the half-life time. When that time elapses again, you're at another half, which is 25. When that same increment elapses again, you're at 12.5. So what's happening is we get this asymptotic behavior. It will never cross the x-axis because you can't ever get 0% radiation. It just keeps having and having and having and having. So the x-axis or the t-axis, the horizontal axis, would be what's called an asymptote. Asymptote. Okay? This is some key terminology we need to know the definitions of in order to successfully complete this section. Do those four things make sense? Okay, I'm going to leave you off with here so you have a night. What we're going to do today is we're going to look at the domain and some asymptotes. So the whole concept of today's lesson, we're going to do 3 lessons about the functions. Then we're going to do a 4th lesson on how to call it together and graph these kinds of functions. So the first thing we want to look at, domain, vertical asymptote, and poles. And what these are, if you look at the images right here, these are domain restrictions. And what you'll notice is that these graphs skew toward these asymptotes that we talked about yesterday. Okay, they're going toward all the asymptotes, but they're never reaching their location. Again, the reasoning, somebody guessed this, they're always the reasoning for question. What caused these domain restrictions?
It's decreasing at a decreasing rate. Well, no, it's because
That was end behavior.
no.
That was end behavior. What causes the domain restrictions?
The denominator can't be 0.
Yeah, when the denominator is a variable, whatever would make that denominator 0, whatever value of the variable, is not allowed in the graph. So I can tell you, look at the far right graph here, please. X equals 4 and x equals 0 are domain restrictions. I know that because I can see that the graph will never get there. It's asymptotic to that vertical asymptote. These are vertical asymptotes at x equals 4 and x equals 0. That's the equation of the vertical asymptote. Remember, the equation of a vertical line is x equals. So again, what we're looking for here are things that would cause the denominator to become 0. Now, let's continue with that. So The first thing we're going to look at is a vertical asymptote. Mike, why don't you read for us? First paragraph, please.
Remember that the domain of the function is values of the independent variable, traditionally x, you take out. When we think about rational functions, we have to look for values of x that will make the rational function fraction undefined.
So the same stuff we've been saying, obviously. So example 1, we're going to figure out what are the values of x that make this rational function h of x undefined. Then we're going to use this information to make a conclusion about the domain, and then we're going to apply it on our calculators. So you're going to see obviously the answers are here. What's the process? Explain it. What are we doing? Look at.
Well, first part is you take the bottom of the fraction and you're setting it equal to 0 in the asymptote.
Yep, so you set it equal to 0, find the discontinuity, which will probably be an asymptote, but we're saying the part that cannot be in the domain. Do we see this? Explain this down here. It's two representations, right? It's word one. What's the difference between the two?
So basically x can be anything except for 2, and on the left it says it can be negative infinity and it's off to 2, and it can be anything past like 2.
But not.
Not 2, and then
Yeah. Okay, so this is an easier way to write this one, because this is not equal to 2. This is useful when you have several ranges of intervals that the independent variables define upon. So maybe you want to write like 2 different things out here. You can define a range instead. But in this case, I would use the one on the right, set notation. Now, go ahead and take your graphing calculator out, please. I want you to do it on there because on your graphing calculator, what you're going to notice is that you don't see these asymptotes. You're not going to see vertical asymptotes. But they're there. And your idea is to find them. Now, if you need, I'm telling you now, you can write this down or just make sure you know to do it. You need parentheses around your denominator, always. Always, always, always. Okay, so go to Y1. Go to Y1. Type in the quantity 2x over 3x minus 6. Again, 3x minus 6 needs to be in parentheses. Hit zoom and then 6, so you get like a standard zoom function.
Wait, what is 2x divided by?
3x, it's right in the middle there. 3x minus 6. Again, making sure you put parentheses around your denominator. Hit zoom and then 6. So all the same graph. Does the graph make sense based on what we've written so far? Explain why now. What do you see on your graph? Yeah, where is it located on the graph? X equals what?
So x equals 2.
Around 2 or 3 it looks like. You can't really tell always, right? But it looks like it's around 2, and we clearly got 2 as a result. Let's go ahead and figure out why this is true. Go to your table. Everybody press second table. All right, we're at the table. I want you to be able to insert values for x. So make sure you're on ask for independent. You're good. It's second first, then graph. Can you type over those or no? Is it allowed you to type on top? No, so you gotta go to your table settings, second, or yeah, you gotta make that ask instead. Can you type in your x values? You cannot, let me know. How about over here? Good? Okay. So here's what we're going to do. Type the number 1, hit enter. Type the number 1.5, hit enter. Type in 1.9, hit enter. Type in 1.99, Type in 1.9999. Type in 1.9999. What am I getting closer and closer to, obviously?
2.
And what do you notice? Look at the y value. What's happening to the y value? It's getting what? Very, very... What? In what direction? What do you say down? What's that mean? Negative. This is becoming a very, very large negative number. Keep typing in numbers closer to 2. Type in 1.999999. Okay, it should be getting larger and larger and larger. Now,
For 1.9999 says 2.
After you get to 5.
well, if you type in 2 directly, it's not going to work. But try to actually type in 2 and hit enter. Try to type in 2 and hit enter.
Error.
So it's an error. Why is it an error? Clearly. Because we just said you can't have x equals 2 if it's a main. Now, go from the other. That was an approach from the left. I'm teaching you calculus. That's what's kind of cool. We learned this whole concept, this approach of limits to calculus. So we approached, here's x equals 2 right here. We approached it from the left, and we noticed our function became very, very negative. Now let's approach it from the right, and we're going to see it's going to become very positive. So type in 3. Go back to the top, sorry, back to the top. Type in 3. Then type in 2.5. Then type in 2.1. 2.01. 2.001. 2.0001, etc., etc. The number is becoming very, very what? Continuing to what? Increase. What do you have? What's the highest number you're at?
2.000.
And what's the y value you get for that?
133,334.
So what's happening again is the graph is growing extremely fast as it approaches from the left. When it was approaching from the right. When it was approaching from the left, it was falling very, very fast. So go to your next page on your slides, please. Okay, that was the concept of what we literally just did. From the left, we got closer and closer to 2. From the smaller number all the way to 2. From the right, we got closer and closer to 2, starting at 3 and making it a smaller value and smaller value until we got to 2.01. Okay, that's the left approach and the right approach we just did. Now, clearly when x equals 2, this cannot be true because you'd get 4 over 0. Okay, so let's see. Sabine, read nice and loud, please, the conclusion for us.
For this example, we can see that the values of the independent variable cause the denominator to become 0 are not included in the remaining function. This means that there must be a
Discontinuity.
discontinuity such as the convertible asymptote at the location. There is another type of discontinuity that we will look at and call a hole.
Okay, so instead of looking at the vertical asymptote, let's figure out when a hole tends to occur. Okay, when a hole tends to occur. Slide down to the next example. So, what we'll notice here, and we can read all this and stuff, what we'll notice here is this. In order to figure out what makes the denominator 0, we need to factor it, as always, because it's quadratic. So if we factor that denominator, here's what it factors into. X minus 6, x plus 2. X minus 6, x plus 2. Well, okay, that's interesting. But what's the numerator? What's the numerator in factor form?
2 times 20 x plus 2.
So what do you recognize? What do you want to do? You want to do something, I know you do.
Cancel.
Yeah, you want to cancel, and I agree, I want to cancel also. Okay, but what we need to do here is recognize something. We can cancel, first of all, we can. But when there's a cancellation, it's an indicating factor of the whole. Write that down. So later on we're going to see it, just jot it down. When a factor cancels, and I wrote this at the end of this paragraph, but I prefer teaching it the other way. I used to teach you with this method first, and then go to factoring. Let's do factoring to make it easier. Factor, if it cancels, it's a whole. Now, here's the thing. The question is, where is that hole in the graph? Where is that hole? Let me explain what I'm getting at. Let me explain. As you approach the number -2 from the left and the right, here's what we see. Can I plug -2 in here? What do I get if I plug in -2?
You get 0 on bottom,
And
0 on top too.
yes, you get 0 over 0. Do you see that? But if I plug in just 6, I get some number over 0. So when I plug in a 6, I get some number over 0. That's called undefined. We've heard of that, right? That's a vertical asymptote. But if you plug in a number like -2 in this case and get 0 over 0, what's that? That is called, and this should say, it's a typo. This should say g of -2. What that is called is an indeterminate value. It's another word for it. I'm going to go to indeterminate the way I've always done. Indeterminate value. What that means is we know that something weird is going on there. We don't know where the hole is or why that happens to that graph. It's not determinable from looking at this. This doesn't tell us 0 over 0. What is 0 over 0, right? 0 is nothing. Can you divide nothing into nothing? You can't divide nothing into something. We've said that before. You can't have 7 over 0. It's impossible. We literally can't divide 7 by 0 quantities. You get infinity, or the idea of infinity. So that's what vertical asymptote comes into play. But 0 over 0 is not very clear. So what we do is this. We do one of two things. Either we take a table approach, and what we'll notice is, look, as we get closer to -2, this becomes around -1/4. As we get closer to -2, this becomes around -1/4. So -1/4 seems like the y value is going to be there. But again, I can't just plug -2 in, because I can't get a y value by plugging it up there. But if I factor it, cancel the factors, I'm left with 2 over x minus 6. I can plug a -2 into there, can I? What do I get when I plug a -2 into here? I get -1/4. The same value you would have gotten had we done the table approach like we did in the last example. So what's happening here is this. You can graph this in a minute, but just to give you an idea. At -2 and -1/4, you've got a hole in the graph right there. Okay, you've got a hole. Now, there's also a vertical asymptote at, where's the other point? 6, right? Yeah, at x equals 6, because that would cause this, right? X equals 6 would cause that to become undefined. So over at 6 over here, sample on that 1, 2, 3, 4, 5, 6. You have a vertical asymptote. There's the vertical asymptote there over at x equals 6. Well, this is a hole in the graph. The reason I know to put it there is because I have a coordinate. The coordinate is -2, comma, whatever I get either from my table approach or from plugging -2 into the simplified form of g of x. Okay, so take a -2, plug it in after you've canceled the factors that cause this indeterminate value. Once you plug that in, you'll get the y value. That's where it's going to be on the graph. Now, before I go any further, go ahead and graph it in your calculator. Okay, graph the original, please. Not the simplified form. Graph the original. Okay, which is at the top if you don't know where it is. Remembering to put parentheses around your entire denominator. Not just the numerator, please. So on your graph, you probably don't see anything weird at -2. It looks like the graph just continues, right? What do you see at 6 in this thing? You got it? Or?
Yeah.
What do you see? You got X. You should get something like this. This is what you should get if you just type it in correctly.
What did I do to that?
I didn't even know. Okay,
You put negative signs there. Is that minus signs? So multiply them by -1. Isn't that weird the way that works? Yeah. So you got this right? So it's obvious at 6 there's a vertical asymptote. But at -2, it doesn't look like there's anything. Does it show a whole -2 on there? Or it shows an negative. Yeah. Alright, so here's what the graph really should look like. Here's what the graph really should look like. Go to the next slide. Okay, and what do you see at -2 on my graph? What did I superimpose? Yeah, there's an open circle there. Okay, see the open circle at -2? So this is really what it physically should be like. It's not a vertical asymptote. It's simply a hole. So here's our conclusion, right? It's a vertical asymptote if it's a factor in the denominator only. But if it's a factor in the numerator and the denominator, which you can cancel, it's indicating a hole. Is that clear? Does everybody hear what I'm saying right now? It's in your notes. I've written that somewhere, I think. So what I recommend you do is you maybe highlight that spot. It's probably right there at the conclusion, yeah. So this is it right here. That's what I just stated, the second sentence. That's what you have for a whole. You can think of this as having the same factor in the numerator and the denominator.
Wait, I don't,
Go ahead.
I got screwed up.
You could think what
Yeah, no, but yes, yes.
you with 2x minus 4. 2x plus 4. Okay? So see the note I put? I put that note there on purpose so you remember that. Don't forget, just because you don't see it on the calculator doesn't mean that the hole is not there. You need to notice that from the function. You can't rely on the calculator for this. By the end of this section, by the end of this whole idea on rational functions, you won't even need a calculator to graph. You'll use it without a calculator. It's actually really easy. All you need are these identifying factors. Okay, these asymptotes, these holes. We're going to talk about horizontal asymptotes and behavior. Okay, once we get through all that, you'll be fine. All right, let's look at example 3. Determine the values of x that cause f of x to be undefined. Classify each of these discontinuities, either vertical asymptote or a hole. So what do you notice I did? What did I do right away? What's the first thing I did? I want to know. Good. I want to know all the factors. So I want to know the denominator's factors so that I can see what values of x make the denominator 0. So look where I'm pointing here. 0, -5, and +2 are clearly going to be, we're going to see them already, discontinuities. But if I notice the factor x, that's what causes x equals 0 to be a discontinuity. These are like the roots of this equation. That's what you're really finding, right? The roots. The roots of the denominator give us the discontinuities, but one of the roots is 0. Oh, look at the numerator. One of the roots of the numerator is also 0. It's the x, the 3x. Right? If x is 0, this whole thing becomes 0. So if I look at this, the x cancels. Okay, there's clearly a hole at x equals 0 because the x is canceled. Whenever there's a canceling factor, what would make that undefined is called a hole. So at x equals 0, we have a hole. At x equals -5 and x equals 2, we've got our vertical asymptotes. So you see the vertical asymptotes with the dashed lines. To find the location of the hole, again, what do? I take 0, or whatever would cause the hole, which in this case is 0, because a 0 here or here makes this indeterminate. Take that 0, plug it into the simplified form. Here's the simplified form right here. Just get rid of this x and get rid of this x. So take a 0 and plug it in. You're going to get 3 times 2, which is 6, over, in this case, 5 times -2, which is -10. 6 over -10 is -0.6. So you're literally taking the value that would create a hole, plugging it into the simplified form. You're doing f of 0, where f in this case has already been simplified. Okay, this is the coordinate for the hole. That coordinate is right here on the graph. You can barely see it. Okay? Any questions? Questions? Does this make sense, this lesson? Is it pretty easy? So if you were to summarize it, how would you summarize it? Of course, today's lesson is like quickness, right? How would you summarize it? See?
Vertical asymptotes, it says if the factor, if the denominator factors in,
Good.
whereas the whole and factor in the denominator cancel.
Perfect. So if the numerator and denominator are the same factor and they cancel, it's a whole. If it's only the denominator, we go ahead and we say that that is a vertical asymptote. How do we find the location or the coordinate of the hole? Because you can't plug in the number, you get error.
Once you simplify the equation, you plug in that solution and find the coordinate for it.
Yeah. So you simplify the equation first, or the function first, then plug in the x coordinate that will create a hole. And as a result, on the next, or as a result, you'll get a numerical value, not an error or indeterminate value. If you ever plug something in and you get 0 over 0, it also means it's a hole. If you ever plug something in and get a number over 0, it also means it's a vertical asymptote. So you don't have to factor, but you're going to sit there and try numbers all day, and just plug them in, it takes forever. So start by factoring so that you can identify and will make the zeros in the numerator and or denominator. Okay, the next page is your homework. Okay, the next page is your homework. There's 2 videos there. If you struggle with this a little bit, I recommend you look at, tonight. I think I gave you 6 problems, right? Yeah.
Yeah.
Go ahead and start on these, please. Okay?
Thanks, Bob.
Yeah. Go quickly. I want you to get through at least 3 of these before you go home. You should easily be able to do 3 of these in 15 minutes. And it's 5 minutes per problem. And the first problem probably will take about 30 seconds. If you forget or get confused, look back. Go back to the notes, go through the steps of the problem, recreate it. Hey, check with the person next to you, you got the same answer once you finish the first one. If you didn't, figure out why and ask me. I'll come over and look. Correct. So if you have two factors, that would be two holes in the graph, and we'll just need one of these. Yeah.
I'm confused, like how to start.
Factor first. Start by factor in the top and the bottom. What if the factors that repeat themselves? Correct. So what would cause the denominator to be -4, right? So x cannot equal -4 is correct for your number. And then you have to identify, is that an asymptote or is that a whole?
So it's an asymptote.
Correct. Now look at the graph. Did you cancel any factors there? So it's an asymptote by fact. Remember, it's only a whole if the factors cancel. So right away you can say that x equals -4, that one right there. You can put right here, you can put our vertical asymptote. That's the equation of the vertical asymptote. X equals -4. But the main restriction is x is not -4.
So only once you figure that out, would you just probably have to calculate?
Yeah, I just want you to graph and take a quick sketch of it. That's all. So guys, all you're doing is a quick sketch afterward on the side. Okay, just put like a graph of it on the side so you can see physically what it looks like. I've told you that before, that like seriously in 8th, 9th, 10th grade, half the time I learned more about math was on my own. When I would sit there and look at a function for homework and just graph it. That's why I have to do that, just so you physically see what's going on. And when you have a hole, guys, obviously what you should do is find the coordinate of the hole like we did in an example. So I think, is that number 3 that has a hole in it or no?
Yeah.
Number 3? Number 3, you're going to have a hole in there. So cancel the factor, come up with a simplified form, and then go ahead and find the y value of the hole. Correct, because there's no factors going there at all.
Yeah.
So number 2, Mike makes a good point, guys. Look at number 2. You clearly know that this has got to be vertical asymptotes because the numerator doesn't even have any factors. So by default, it's going to be 3 and -3 there. Yeah, so just graph on the side for each example. Oh, you want me to check them in? Hey, question for you guys. What do you think, actually before you graph it, you don't have to answer this out loud to yourself. Before you graph it, on number 5, hypothesize what that function looks like. Try and like picture in your mind what number 5 probably looks like before you graph it, and then graph it. You'll probably be surprised. Think about it, and then graph it. Try and think about what it would look like, but then graph it afterward. It's going to be something weird looking. Guys, these rational functions all have this kind of like weird curls to them. Okay, and the reason that happens is because of the asymptotes. The asymptotes are like boundaries in the graph. You can't cross them. It's really cool looking, yeah. It makes some interesting images with it.
I didn't see it, but it's like looking at figuring out how to hold it. You can't get out. Was it if you want? Sorry.
Where? Yes, we are. So what does it look like? Which is why. I see what you're doing. It's the function of R is equals to the next functions. Use x as the t. That's in the numerator. You keep solving the numerator. The function is x equals 4, so you know what that is without a function. Y equals x minus 4 is a. So reference it. It's because the cancellation doesn't get it. Look at the actual function. Guys, again, graph all the originals. Don't graph the simplified form, but look at the simplified form to help you think about what the graph will look like. Is that what number 2 looks like, by the way?
Yeah.
What does number 1 look like? I know there's a vertical asymptote of -4. Is it increasing like this on the left, like that? Decreasing, thank you. And then it's increasing on the other side. Like that, something, right?
I got the other, was it other way around?
Yeah.
The other way around.
Yeah, so we click the last one, 3-0.
Say again, Mike?
So it looks like the last one, 3-0.
It looks like the line is at 0.
Wait, wait, wait.
Check your number 3 to make sure you got the same. Please check your whole portion for this one. So the denominator factors in at u plus 7, u minus 4. U minus 4 is cancel, which tells us there's a whole of 4. Vertical asymptote negative 7. Here's the simplified form. We take what we make it a whole, which is 4. Plug it into the simplified form. K of 4 is 1 over 4 plus 7, or 1 over 11. Here's the hole's location and coordinate. Here's the vertical asymptote. Okay? Finish these up for homework, please.